you. All right, so we had some technical issues with Mac and Windows machines. We resolved that, obviously. So I'm very happy to have Ingrid here today. She's a professor at KU Leuven in Belgium. She within the research group COSIC. She is highly recognized for her pioneering work on hardware security and embedded systems. She's a fellow of the IEEE and ISCR and a member of the Royal Academy of Belgium for Science and Arts. She received 2 advanced ERC grants in 2016 and 2021, and her most recent awards are the 2023 IEEE Donald O. Pedersen Solid State Secret Awards and the 2024 EDAA Achievement Award. And just this year, she received another award, the FWO Excellence Prize in Applied Sciences. So this is an award, I think this is granted every 5 years. It's also often referred to as the Flemish Nobel Prize, so congrats on that. And exactly, I'm done. So finally, she's very well connected to industry and a co-founder of also the startup Belfort. Yeah, but let's welcome her and thank you for being here.
Hello, hello. Okay, works. Yes, so I'm not able to use this slide, so I'll just check there. So welcome, and we might give half of the presentation today and the second half tomorrow, if we continue like this. So I'm going to talk about hardware implementation challenges for post-quantum cryptography, general topic, and since we have so many experts in the room, what I actually want to do with this presentation is I want to give you some challenges to work on, things that I think are not solved. And I will show some results we have, but if you go and follow the sessions at CHES, you might learn even more. So I will have a very, very short introduction on post-quantum cryptography. Don't think you need this here. But I'll show how we usually address when new crypto appears. We've done this all. The first thing we usually look at is feasibility, make it possible. If you come with, if the mathematicians come with new schemes, how do we implement those? That's kind of first stage. The second stage is how to improve performance, throughput, latency, area, power, energy. And I'll especially focus in the presentation on the difference between throughput and latency and also power and energy. I think power and energy are really a challenge. And then the third one is secure implementations. We want to protect them against side channel fault attacks, microarchitectural attacks, and any combination of those. And so the challenges I will cover is new generation of attacks. And then for this audience also post-quantum, now we have the key encapsulation and digital signatures, the masking challenges. And then the third topic, so it's 3 topics, is computing on encrypted data, fully homomorphic encryption, which is actually also post-quantum secure. It relies on lattice-based crypto. And I do want, I have a semiconductor background, link it to this report. It's a bit older now, it's 3 years old. It's from the US CHIPS and Science Act. And when you read that document has, it's only 25, 30 pages, not more. It has a whole section. This is the section on semiconductors and system security. And I'm not gonna read this, but the first thing it talks about is every aspect of the system must be considered. That's not new, I would say, for this audience. Should be robust against side channel attacks. So the Office of the President knows about side channel attacks. Security must be pursued as an integral part of design, not as an add-on after the chip is designed. This is something also we advocate for the last, I don't know how many years. Open source security looks like the best approach for innovation and transparency, but still quite unpalatable to the industry. And we do have workshop yesterday, presentations, and so on. This community, which I really like, is working on open source, is also putting the results with artifacts on GitHub or whatever, right? And so then there is a section and the 6 topics people should be working on. And I would say these 6 topics, that's something we at COSIC have been working on for the last 20 years, I would say, but it's also what the CHES community is working on. And so I'm going to use this as a connection between the different sections I'm discussing in this presentation. The first topic there, it says implementation of post-quantum cryptography. For this audience, I probably don't have to introduce you, but I found these 2 nice pictures. On the left, a recent result from Microsoft called Majorana. On the right, recent results of Google, which I call Willow. And as you know, it's quantum computing, it's new technology, it's based on quantum mechanics, it works on entanglement, and it's, for us community, extremely efficient for some mathematical problems. And so we know that older algorithms already, Groves and Shorts, will break some of these schemes. We know that symmetric key will need double key length, hash functions also double length, but we're working on post-quantum because the RSAs and the ECDSAs and so on, they're completely broken. And so that's why NIST started this. And now we call this the first challenge is us implementing this. So NIST so far has standardized 2 algorithms, one for digital signatures, actually 3, one for CHEM, 2 for digital signatures. So far so good. But what we see as implementers is, first of all, there's multiple schemes. And multiple underlying mathematical constructs, which makes it tougher to do it in hardware. We want these implementations efficient in hardware and software, not post-quantum, but just in regular semiconductors, have to replace the old non-public keys, public key, and they should be resistant to the non-quantum current side channel and fault attacks. And it doesn't stop there, in the sense that this is a screenshot I took from a presentation at NIST this March, and they call it Post-Quantum Crypto, the Road Ahead. And you see to the left, they already approved 3 standards, ML-Chem, ML-DSA, and the last one, based on Sphinx, SLH-DSA. They have a 4th one they want to approve. In their March presentation, they said it's hopefully by the summer this is a standard, but it hasn't come out as far as I know. And that's a really tough one to implement. It uses some floating point numbers. There is a new CHEM, HQC, Hamming quasi-cyclic design, and I learned already this morning in a session that this uses non-power of 2 entities, which we have to look at. And then there is so many new candidates. We need to implement all of them to verify. So there's, and all based on different mathematical schemes. So there is the unbalanced oil and vinegar schemes, there is MPC in the head schemes, lattice schemes, symmetric key, isogeny based, and so on. So that's our first option. That's, I consider, part of the feasibility. These have to be implemented. But then they need to be secure, on top of that, against various forms of attacks. And so far, I haven't seen anybody who has done a nice masking scheme for floating point numbers. That's going to be a challenge. And side channel attacks, we're doing this for the last 20 plus years. And so we've evolved since this very first implementations we did at COSIC. This is something from 2005, a very simple timing attack with a loop antenna that the students made themselves. But I hope this pointer works. Yes, that you can see this is elliptic curve implementation. Key bits 1 is longer implementations than key bits 0. Since then, we have evolved a lot. We've done many types of side channelized power, electromagnetic, microarchitectural attacks, cache attacks, transient execution attacks, many types of fault attacks, EMs, lasers, clock, voltage glitch, remote and local And of course, as an attacker, I'm allowed to do any combination of that. And so countermeasures also has been evolved for a long time. This is an old work we did in 2004, and I noticed in another session this morning that people are still using it. But what I want to focus on, okay, move forward, yes, focus on is some of the latest attack vectors, and our implementation should also resist those. And I start for that for Spectre. Spectre and Meltdown was like a new type of attacks published first 2019, 2020 round. And actually what Spectre does, it abuses the speculative execution of microprocessors. So many designs we see here are implemented of simple little microcontrollers, and we as implementers have control of what that thing does. But these advanced processors, they have a mind of their own. They execute in an order they want themselves just for performance reasons. And Spectre came out, it has several variants. It applies to all high-end processors, Intel, AMD, ARM, and so on. It abuses the reads or the leftovers in the cache or in the instruction pipeline. And these Spectres or these meltdowns now can be even combined with electromagnetic attacks or other side channel attacks. So Spectre EM is the work we did where we do EM side channel attack within the transient execution window of a Spectre attack. And the last one would also show is BADRAM. So how does this work? It's a physical transient execution attack. And so here you see a typical setup. So you have, in this case, it's an ARM Cortex-A72, and this is EM with a nice probe under the stepper table, or even a simpler setup with the probe like this. Both cases, it works. And what can you see? That you actually see during the transient window, you can see what's being done in the EM field. And in the left, you see a UDIF instruction, and you see that division by 0, which takes 4 clock cycles, or division by -1, 6 clock cycles, has a different power spectrum. Division by 0 has one peak, say for instance a bigger peak at 150 megahertz. Division by -1 has multiple peaks like 100, 250, and so on. So out of this frequency pattern, you can figure out a transient operation, which might not even be what might be retired before, not actually executed. Same for control flow dependencies, nested branch prediction. If you do a correct prediction, you have a different power spectrum than with a misprediction. And this can now be abused, and so you can do your regular EM information retrieval from this kind of transient windows. And the tough part to fix this is that you don't have control of what the pipeline of this processor is and how this processor implements this. This is even not published. Another recent attack is called BADRAM. And what you do there is you trick the processor in executing or assuming it has a different memory map than it actually has. And this is actually an attack on trusted execution environment. So what is a trusted execution environment? We don't have many papers on TEEs here at CHES, and I think we should have more. This is a topic which is very interesting. So a TEE is a root of trust where you trust that a certain part or one particular virtual machine is protected from the rest of the system. So, and without a TEE, the cloud provider has full access to these virtual machines. So in this case, for instance, you see 2 of these virtual machines. Now, a TEE will lock out the cloud provider, and it will enable computing on private data. So the data belongs to this specific TEE, and the others don't have access to it. But if you do, there do exist, and I'll show that, some attacker models that really enable a vast amount of attacks. So how does it work? So you have a CPU, it has a BIOS, and it talks to the memory DIMM, and the memory DIMM has a little processor, SPD, which tells you what's the configuration of the memory. So you can see here to the right the setup. There's a PhD student in our group, Jesse, who made this, and this whole setup is $10 to $50, not more than that. So what happens is that at startup, the BIOS will read that SPD, and SPD will reply on how large its memory is. So in this case, it says, I am 16 gigabytes large. And then it will configure its memory controller so that you have a correct mapping from the physical address space to the DRAM address space. So this is a normal operation. So, but then what you can do simply modify that SPD, and because that's information which is not checked, and that thing is going to say, I'm actually 32 gigabytes large. And so 32 gigabytes large means that you now have a mapping of two different physical address spaces to the same DRAM address space. And this is the whole concept behind BATRAM, that in this way we actually break the TEE assumption of having separate memory configuration, separate memory regions for different virtual machines. And so this is the results, and you can see multiple TEE setup or implementations. The first one, Intel Classic SGX, that one provides you with confidentiality, integrity, and freshness, but it's absolutely not scalable. It only works smaller memories, 256 megabytes or so. The second one is larger, but does not provide integrity. Freshness is broken. The Intel TDX does have some integrity checks and is scalable. And that one works because they use some extra, they use some of the ECC bits, and the ECC here is error correction and detection chips for this integrity. But the practical demonstrations are done on the AMD TEE environment, so that one is also broken. So you don't have integrity. It works for the latest memory interfaces, DDR4 and DDR5, and this has gone through responsible disclosures, and so AMD now has some firmware patches, but in my opinion, this is only the start of this kind of work. We're going to see way more attacks. And this is, we saw something this morning also, actually an access control attack, right? And so, so that approaches the secure against various forms of attacks. But now I'm going to combine this with post-quantum crypto, which we won't resist, and I don't always have a solution, but I'll show you some of the challenges there. So we fixed all our timing problems. The code is constant time, and now we want to mask. The masking people might consider this quite simple, but basically if you mask the Kybers or the Sabers, you have two types of masking that you need, the arithmetic masking and Boolean masking. Boolean masking means you split your secret in Boolean shares. Arithmetic masking means you split your secret in arithmetic shares. Every execution you need new randomness. And what we have seen is there's so many types of masking, Boolean, arithmetic, inner product, threshold, and so on. They all start from similar leakage models, is that the shares leak independently, and this is something we really have to look at, because I think in deep submicron this assumption might not hold anymore. They all require randomness, and we see quite some work popping up where people try to reduce the amount of randomness. And I had want to show some results of two experiments. One was an AES masking on microcontrollers, but this is post-quantum, so you'll have to go to our COSET presentation there. And here I want to focus on the cost of masking post-quantum lattice-based encryption and all the issues we're going to have if we also want to mask all these other schemes which are not lattice-based. So that might still require a lot of work. So we have a double challenge. We want this to be both efficient, feasible, and masked. And I start with Kyber Sabre in construction, and the key encapsulation mechanism is one where they use what's called the Fujisaki-Okamoto, I hope I pronounce that correctly, or FO transformation. And they do that to make it chosen cipher attack resistant. And basically what it means is that you don't simply have a public key and a secret value which you encrypt to get the ciphertext. No, they do, to be resistant to chosen ciphertext, they actually have, starting from the secret key and the ciphertext, you create an R prime, re-encrypt it, and those two ciphertexts should be the same. And that's what FO will check, and this FO is the same in Kyber Sabre and maybe more schemes. So this is a bit more zoom in, and so you see the secret here, you see the ciphertext popping up here, you see the R value and the message value coming out. You re-encrypt, which is all this part. You get ciphertext out. Here is the FO comparisons. If this is the same, you release the key. If this is not the same, you release basically random values. Whether it's Sabre or Kyber, it's very similar. So this result was at the time that we were looking at implementations for Sabre. The two main differences between both schemes is that Sabre uses powers of 2 as their Q value, and Kyber uses a prime number, 3329, and Sabre uses for their noise and error sampling a rounding scheme. We hardware people like rounding because explicit errors are way more expensive, and that's here that you see these explicit errors being added to the ciphertext. And so for these schemes, people use both arithmetic and Boolean masking. And parts, like all the polynomial operations, stay nicely. You can mask them with arithmetic masking. There's many papers on that topic here at CHES. The hash functions and any variations of those, you mask with Boolean masking. But then as a practitioner, I have the problem that I need to convert from Boolean to arithmetic and from arithmetic to Boolean, because we use both in our Kyber or Sabre schemes. And those are the expensive operations, so that's why I want to focus on those. And of course, these conversions should never disclose or go back to the original secret. So you have to do this in the remain masked. So this is some first experiments. Is the cost of one of such arithmetic to Boolean conversion. Maybe now it can be done a bit better. But you see, yellow I'm using for arithmetic masking, grayish bluish I'm using for Boolean masking, and so somewhere between those two, between the arithmetic and the Boolean, you have to do conversion. And then at the end, you have to go from Boolean to arithmetic back. And this final FO check is in the Boolean domain. So one solution we came up with is, but you see how expensive this is. This is for one of these conversions. It's around 50,000 cycles, and this is on one of those small microcontrollers for 2 shares, 150, 170, 200 cycles, 3 shares, and so on. So this is a very expensive operation, and this is a bit feedback to the mathematicians there. Please consider not too many of these conversions, right? And so this is the message I want to give here. not the exact numbers on how much it costs, but how much extra it costs to get your convergence, right? So Saber or Kyber unmasked is a bit similar cost implementations. First order, you see, is a factor 4 to 10 times more cycles you need. Second order sits 7 to 15, third order, and so on. And this is the amount of random bytes you need. Why is this? It's a bit better for Saber, and that's because we use this power of 2 arithmetic, and we use rounding instead of explicit error sampling. And that's the difference in the cycles. So that I would say that power of 2s are more masking friendly, right? And so this is a bit an exercise we recently did, is that we compared, tried to find some learning with rounding schemes which are masking friendly compared to learning with error schemes. And you see results, Kyber, Saber, and then 3 versions that Suparna and co-authors made. They called it Floret, Espada, Saber, and one is a bit more cycle-oriented, the other one is a bit more memory optimized. But you see that by looking at the problem by itself, that you can gain quite a lot. Oops, one more. The other thing now is that we have problems that this arithmetic to Boolean conversion, which is very expensive, is actually now a weak point if you want to do fold attacks. And so here you see a masked version, and now this time it's Kyber, because this more recent result, and you see you have more of these parallel paths because we do want this explicit masking of these error terms, right? And so you can do a fault attack on such a side channel attack protected Kyber, and it's the arithmetic to Boolean operation that's the weak point. And higher order masking won't help it. So you need here combined countermeasures, and at this moment I don't have, or we don't have a solution for it. This is a challenge to work on. And then there is multiple other schemes which are non-lattice based, which don't use maybe this FO transformation, but they have some kind of weird other operations. And one example is, for instance, the Gaussian elimination. And the Gaussian elimination seems to be an operation which is used in all these unbalanced oil vinegar and other code-based schemes. And Gaussian elimination is something we learned in high school. It's a matter of pivoting the rows until have lower diagonal, which is completely 0, and then you can do back substitution. The problem is that now I'm going to do this in the masked domain. But in the masked domain, I don't know if my masks represent the value 0 or not. And so that's where you lose. Or becomes the difficulty. So you have a simple system of linear equations in many of these schemes, but I'm doing this in the masked domain, and now I have the difficulty of figuring out that some of my pivot elements are 0. And you see here what's the cost of doing this. This was on ARM Cortex M4. And the extra cycles for first order, second order, third order. So in my opinion, this is really expensive. So probably lots of progress can still be done there. This is one example. And so what we're trying to do now is for many of these non-lattice schemes, figure out what are their basic operations and how I'm going to have these basic operations protected against side channel attacks. And then fault attacks, and then a combination of them, and so on. Now brings me to the next topic. Leaves you with some challenges. And the next topic is we want low power and low energy, because those two are different, cryptography. And we've tried to do that over the years. It sits in my category feasibility. We have to have reduced the throughput, the latency, the power, and so on. And so we've done that over the years for many schemes, but I think we now have to do that for lightweight crypto, say for instance for memory encryption, for FHE, fully homomorphic encryption, zero knowledge, and many other schemes. And to emphasize the importance of reducing the energy, and certainly if we want to do that for fully homomorphic encryption, I actually, because I don't have numbers for FHE, I want to go and use the analogy of GPU cost for AI. And the data I'm using this is my interpretation, I got from a hot chips tutorial, very recent, 1 month ago, less, about how to design the racks of data center. It was very eye-opening. And the second document I'm using, and I'm now combining those two, is an article in The Economist of the end of August, NVIDIA's big short circuit, too many chips, too little juice, and you'll understand why. One Blackwell GPU consumes 1 kilowatt, that's known. 4 Blackwells and 2 CPUs sits in one tray. And at this hot chips tutorial, they showed, I mean, it's a picture I took, one of those trays. And all these shiny things, that's copper, and that's copper because these things are water-cooled. So you see all the water pipes here, and this is 1, 2, 3, 4 of these Blackwells. There are, here, there are, 18 trains in a rack, so add it all up. It's 130 kilowatts on GPUs and CPUs. There is 2 CPUs, plus 160 kilowatt cooling, so that's around 300 kilowatts for one rack. We don't know how many racks are in the center. That's probably private information. But then this Schumpeter article says that NVIDIA will probably have 2.7 million Blackwells they sell in 2025 and 2.4 of these GB units, which is kind of this combination. Now, if then extrapolate this, that will require to operate them, because you can buy them, but if you buy them, you should also use them. It requires, in the US alone, 25 gigawatts of extra power. I mean, how many nuclear plants are these? That I don't know. And so that article was also saying that there's currently 23 gigawatts installed. It shows you the importance of energy reduction. And I think if we continue like this, this is going to be an ecological disaster, a bit like Bitcoin mining. And so these were the pictures I took myself. You see a zoom in. This is all copper infrastructure. You can imagine you cannot have water leaks. There's special infrastructure to make sure that these things don't leak water. And so your sensors are on top of the rack. Because there is so much copper, these racks are extremely heavy. And so there's mechanical engineers that have to figure out that the racks don't bend on their weight and so on. It was kind of cool to see all of that. So that's a bit zoom out. That's one of the pictures they showed of Meta's Catalina, which kind of uses those in a slight variation. This was another one, Google TPU data center, but we don't know how many is in there. So I think this is a message. We want to reduce the energy consumption and the power consumption. And how do we do that in hardware? We actually, I want to show this for FHE, but in general, how we do that by going domain specific. Focused processing. GPU is too general purpose for me. For an introduction on FHE, so what is computing on encrypted data? Basically, what most of you will know is you have data owners. The data owners encrypt the data. Only the designated party can decrypt, like this person can decrypt, this user can decrypt, provides you with end-to-end confidentiality. So the compute server or the cloud does not own the key. So it can perform operations, but it cannot decrypt because it doesn't own the key. As many application domains in finance, in health, industrial, digital twin, It's a big topic on to apply this for AI, which then goes on top of. Then you need 2 layers of cloud computing, one for AI, and on top of them, one more for FHE. That's not going to work. So what is the cost? The cost is that it's slower, around, depending on what's your reference, 10,000, 100,000 slower. It has high energy and server cost. So the TCO, they talk about total cost of ownership, is high. It's tough to use because current tools lack user-friendliness, and there's quite a lot of ongoing research. The nice thing, it's post-quantum secure, and because the cloud cannot decrypt your data, it really unlocks new value. Your data can sit there, but even if there is subpoena or someone asks for the data, you can give it, but you cannot decrypt it. Over the years, we have done lots of attempts, and it's still a challenge to get these FHEs working. One of the first one was called YASHE. It was a somewhat homomorphic encryption scheme. And since then, that scheme has been broken. We made some implementation for the FV scheme from Van and Verkouteren. We tried then the BFV scheme. And then 2 recent big projects are a CHES implementation, which was part of DARPA DeepRive, and then the TFHE implementation, which is part of this ERC Grand Belfort, and which we're now trying to put in this startup. And then, but this is not the end. People are looking at newer implementations, and Jonas later this week will demonstrate how he implements this for the final scheme. What is this challenge there for the hardware designer is that the FHE community has not decided, there is no standards, has not decided on what are now the sizes and the parameters I have to support. You don't have to understand what these terms mean, but what you have to see is that these numbers, word size for instance 64-bit, the dimension 918, this number keeps on changing. The polynomial size is now around 2000 and so on, but these are not fixed. And then it just recently appeared on EICR Imprint, like a new version of CHES bootstrapping. And there, the security parameters even change whether you want a latency optimized or a throughput optimized implementation. And so it changes a lot in the sense that the dimension goes from 2 to the power 13 to the power 15. That's a lot, right? And so we as hardware designers, they expect us to implement all these versions. And so one way to combine flexibility with performance is what I call domain-specific processing. And domain-specific processing allows you to do this, and it actually was a topic of the Turing Award from Hennessy and Patterson in their acceptance piece. And they say there's going to be a new golden age for computer architectures. We're going to have domain-specific hardware-software co-design, enhanced security will come out. I haven't seen much of that, but open instruction set and agile chip development. So let's look how to do this. This is a slide that I'm using in my class, and as I say, if you go ASIC, you get the best performance per energy unit, but you don't have flexibility. FPGA is a bit better. It gives you some low-level flexibility, but it's tough to have the really high-level flexibility. So CPU is best for flexibility. GPU, this is what in general is called software, but this is not binary, ASIC or CPU. You can have variations in between depending on where you are. And the first option, which you often hear, is what we call tightly coupled, and it's actually instruction set extensions. Already this morning, in one of the sessions, there was a paper on instruction set extensions for post-quantum crypto. So the same can be done there. So what's nice about instruction set extension is actually that you reuse the CPU infrastructure, say from AES, from ARM or for RISC-V, but then you have some instructions not filled out, and you can add your own instruction hardware there. Some nice examples is, for instance, the AES instructions which were added to Intel processors and other. I think that's a beautiful example of dedicated instructions addition. RISC-V gives you this possibility, and like the Basilisk chip which we made under DARPA DeepRive is actually call it the domain-specific processor. But you have more than just this tightly coupled option. You also have what's called loosely coupled. This is a picture which I took from a instruction book of Patrick Schumann. You can decide to have something which is on a local bus. You can decide to have something that sits on a peripheral, that's in a PCIe connection, is memory mapped, and so on. So now what's the best there? It really depends your application. And so one we figured out is, or we designed, is the one which we use for TFHE. And in TFHE, there is two functions which are responsible for more than 98% of the calculations. It's called the key switching and the bootstrapping operation. And if you have those, you say you have a TFHE library, everything is in software, some finance applications or whatever application, you have a couple of operations, and then the key switch operation and the bootstrap is the one which we will put in a coprocessor, and it's the one you want is to be computation constrained, so the communication to your coprocessor should not be the bottleneck. So in this case, it's called FPT, fixed point acceleration for TFHE, and that's the one which will sit on the FPGA. Just those two operations loosely coupled. So it's a streaming solution. You continuously execute the key switch bootstraps for any given input. It doesn't have compiler instruction set, command set settings overhead. It supports both, if you're familiar with TFHE, booleans and short ints. And you can beforehand in your, if you have an FPGA mapping, you can program any, because it's called programmable bootstraps. And that sits in the part flexibility versus performance, right? So how was decided, or what this one, would this one be a good option? And you have to think then on how do I support flexibility? What kind of flexibility do I need? Is it flexibility down to the microarchitecture level? And if you take flexibility border to be the instruction set. The instruction set is the contract between hardware and software. But an instruction set is decomposed in micro-instructions. Those are not available to the programmer. But what's the right level for that instruction set, right? And for fully homomorphic encryption, we have to think about the same thing. What are the high-level operations, addition, multiplication, that we support in the FHE domain? And seems to be the way to go for TFHE. But I showed before, depending on latency or throughput or other optimizations or leveled homomorphic encryption, your parameters change in CHES. That's tough to support, right? So an application should not directly worry about the underlying crypto or arithmetic. And so the way it's solved in our FPT processor is actually that you tell it only that now, sorry, but I'm going to do the calculations on the FPGA. So the FPGA key is a server to FPGA. You specify how many FPGAs in parallel you're going to use. In this case, it's 4. And then the rest of the program is the same. So you have A is an encryption of 1, 2, 3. B is an encryption of 4, 5, 6. And the result is, for instance, multiplication of those two. So it's no change from CPU to FPGA. Okay. That's one thing. What's the right level of granularity? The other option you have to look is what's the time scale? The time scale of your flexibility. At what level do you reprogram? At application level, what happens if there are a new FHE version? What do you do if you have new security parameters? And then you have options. I can have a new input for the same program, we call that a rerun, and that's typically, call it reconfiguration in seconds. You can have a new program, so new security parameters. Maybe you have to recompile your software. That might take hours. If it's really in the hardware and you have to reprogram and resynthesis the FPGA, that might be 1 day, knowing how difficult or how easy tools from AMD Xilinx or Intel are these days. If you actually have to redo or refabricate your ASIC, that can be multiple years. But ASIC is still, as we saw, the best for performance. And that brings me, and again, I don't have the numbers for FHE, but I have the numbers from a designer, Andrew Putman. He showed this at some DAC conference. He's from Microsoft, and he made what's called a NPE, Network Processing Engine. And he says, actually, the performance of, so to the left you have the performance scale, the performance of an ASIC is going to be better than the performance of an FPGA. And that's stated. But the problem is that it takes some time. Over time, this performance advantage might actually disappear depending on how much change there is in your application or your parameters or in your design environment. So under a light change, the ASIC will keep its performance benefit. But if the heavy change, at some point FPGA FPGA superior will show up if you have a heavy change. So yeah, maybe you should take that into account during the design. And that's what he says, that's a problem these days, because making an ASIC takes so much time that by the time it comes out, it might already have lost its benefit. And so he calls that the development phase. And so you have planning phase for your ASIC, then you have development, deployment phase, and then already from start to actually being used. And so that's the benefit of the FPGA, that the superiority really depends on where you are, if your demand still matches what you originally have designed for. So that's why I think in my opinion, at this moment, we're still doing FHE experiments on FPGAs because we don't know in what direction all these schemes are evolving. But we do know that we're way more energy efficient compared to GPUs. And then the last topic, doesn't want to go back. That back? Okay. The last topic I want to talk about is that if you have fully homomorphic encryption, then you actually have to tune your application to the FHE design or FHE constraints. It's not really constraints, but in the sense that if all your data is encrypted, you cannot do an if-then-else, which is data dependent, because you don't know what's the value of the if-then-else, right? Or you cannot have a loop where the end of the loop is stopped based on some condition. Now, we have learned a lot from constant time programming, which we do anyway. So constant time program is also not going to have an end of the loop, which is data dependent, because that leaks information. So you see how your application needs to be tuned to be FHE friendly, or the other way around, right? Make sure that many applications somehow can be matched. And this is, for instance, also the case. We worked through an application which we call fuzzy matching. And the original algorithm is called Levenstein, but our variation is now called Löwenstein. Can I move? I think the battery of this thing might have. So it's not exact matching, it's called fuzzy matching or similarity scoring, depending on what your application is. It has slightly different names. For instance, it's very useful in DNA matching. It's a highly private operation, And still, it would be cool if you can do DNA matching in the encrypted domain. So you never have to give away your own DNA to do some matching. Name matching is a bit similar. But string comparison is a bit more complicated than just calculating Hamming distance, right? Hamming distance, for instance, between John Doe and John Doe, we'll say in this case, this is a difference of 6, which actually we as humans don't see it that way. We actually say this is the edit distance, and this is a more natural match would say this is only a difference of 1. And so how can you go from one to the other? You'll have to figure out the edit distance says this is one distance. How can I go from one representation to another one simply by the number of deletions, insertions, and substitutions? And this fixes a lot of spelling errors in names or spelling variations in DNA, or an accent missing, or translation from one language to another, and so on. So, and for this type of fuzzy matching, special algorithms have been developed over the years. And so we took those algorithms and looked on how can we make them FHE friendly. This thingy is not working well. So one things we did is we work with small variations. Instead of storing the absolute value, we actually store or calculate with small differences between the previous and the current, -1, 0, 1. We use in the FHE the programmable bootstrap to extent. We had some challenges implementing equality check, which is not easy in the FHE domain, and so on. But you can do some optimizations. And so this case study, the first design, straightforward compiled with the Zama compiler, which is a compiler for TFHE, gives you, for one name matching, takes 241 seconds. If you optimize the algorithm, and WF is Wagner-Fishner algorithm, you can already get a factor 3 out of it. If we use our own Löwenstein algorithm, and this is just algorithm optimizations to make it FHE friendly, you get a speed up of 300. And this reminds me of my own advisor, and he would always say, most benefits are at the top. If we do then look at implementing this, and this will come somewhere next year on the Belfort FPT hardware, we think we can get another factor 50 out of it. So this brings some of these applications closer to actual usable applications, right? And what we see in the community is that there is a whole value chain, an ecosystem appearing on these topics. So you have companies which provide applications, you have software providers, the three most famous are Zama has its compiler for TFHE, Google tries to be an open source environment, a multiple scheme, OpenFHE, something similar. You start to have quite some hardware accelerators, like Konami, Belfort, Optalicit, Niobium, and then running this on cloud. So our FPGA solution sits on the Amazon cloud. And you see, for instance, even at Google, there is this HAIR project, homomorphic encryption intermediate representation, and actually for me, this is a design environment for FHE where you can experiment. So say it's compiler tools, tool chain, using IDs for fully homomorphic encryption to accelerate research and lower the barrier to production. So, and then this is a typical picture of their environment. So you can start with different input schemes. You go through all kinds of compiler phases, and at the end, you can implement it on FPGAs. Which brings me to my last slide. I think I catched up some time from our disasters. Is a couple of challenges, I would say. This is post-quantum crypto. So NIST has these nice new algorithms, but this community has to work on making them attack resistant. And there is going to be a mandatory transition, so we better be ready. I also do think that we see a lot of attention these days on TEEs, where the trust relies on the hardware, on a very few number of manufacturers. There is no mathematical guarantee, and I do think there's going to be way more attacks than the two that I showed with Spectrium and Batram, and it's a research trend research topic we keep working on. And then computing on the encrypted data could be holy grail. It's fully homomorphic, so it's post-quantum secure. No secret dependent operations in the cloud, but I do think an ecosystem is forming on this topic. And so I would reply to this document that we're working on it, and the CHES community is working on it. Although there are some topics we should still do more, like the supply chain security is one of them. Thank you. That's my last slide.
Thank you so much for this presentation. I mean, we are a little bit behind the schedule, which I think it's okay. We have a session afterwards with 2 papers only, and then a coffee break before the excursion, so that's fine. I would say let's give room for one question, and I think you are around, so if there are further questions, we can take that offline. Are there any questions for Ingrid? If there are no questions now, that's great, because then we will take questions that you may have offline, and I would say let's thank Ingrid again for this great presentation. Thanks that you have you here.